Hello and welcome to my Lab 5 Physics 1 presentation, and in this video we're going to go over the introductions, the goals, the process, the outcome, errors, important concepts, and finally a wrap-up. Now first off, for the introduction, in classical mechanics the concept of a point particle is often used to simplify the analysis of motion. A point particle is an idealized object that has mass but occupies no space, allowing us to ignore rotational and internal structure. This simplification is useful when an object's size is negligible compared to the scale of its motion. However, real-world objects are extended systems. They have spatial dimensions, mass distributions, and can rotate or deform. Understanding the behavior of extended systems requires accounting for these complexities, such as the moments of inertia, torque, center of mass motion. This lab explores the key differences between treating an object as a point particle and analyzing it as a real extended system, with a focus on how these distinctions affect the dynamics of motion. Now, next up for the goal. The goal of this lab is to analyze the differences in motion between a point particle and a real extended system, as I previously mentioned. By comparing the theoretical predictions and experimental observations, we aim to better understand when each model is appropriate and how the extended nature of physical objects influences their dynamics. And a good overarching question to kind of sum up everything so far is, how does treating an object as a point particle versus an extended system affect the analysis and prediction of motion? Alright, now for the process. What was used? Well, first of all, I found a YouTube video that I will show you shortly, and then got a clip from that YouTube video and put it into the tracker program to analyze the motion itself and the velocity, and then finally applying Newton's laws of motions. Now for the actual video, I'll show you now. This is the video I found on YouTube, and I thought it would be cool to kind of do something different. This is a bow being shot underwater. So this is a non-typical gravitational environment, which I thought was interesting, and just kind of a unique environment to look at. But as you can see, in your typical environment, you, as a point particle, you would just have gravity, and then the velocity affecting the object, and obviously the height and where the arrow lands. But in this system, we have an arrow that is rotating, it is underwater, and it just has a lot of unique forces acting on it, especially with the spin and it being underwater and gravity not having as much of an effect and having a lot more drag. So, as you'll see, I couldn't get a really good tracker graph because there's two little frames to analyze it, but like I'd get a point here, a point here, a point here. So like this would be what it would look like if it were to, or once it reaches that little orange blob that you saw, which I think was a water bottle. And then this is what it would look like over time as it would travel through water. I just added this so you could see what it would look like and how quickly it slowed down due to the drag of the water. And then just a quick thing to keep in mind is that there's many types of arrows and stuff. So, and they have different speeds at which they are launched in the water. So this graph can change drastically just by a 50 grain arrow difference. Oh yeah, and then real quick, I'll show you the tracker program as well. So this is what it looked like underwater. This is your axes right here, just to simplify it so you don't have any plus y hat direction. It'll only be falling. And then you can see just over here that the water ball is over here, but I couldn't capture the whole thing in the video, so that is one of my errors as well. Alright, so some similarities and differences between the data and model predictions. What was correctly predicted was the difference between the forces acting upon the point particle versus a real system. So basically just summarizing that there's a lot more forces acting underwater on the arrow than if the arrow were to just be traveling as a point particle system. And then, like I said, gravity being less influential, however, drag being greatly increased. Although the arrows are aquadynamic, they're much better suited for the air and do face a lot of drag underwater, especially at higher speeds. What was unaccounted for? The changes in the z-hat axis. So it was very hard to see in the video, but it was actually like kind of pointed a little bit away from the bow, so it was almost as the arrow is being shot just a little away from you. It shows that better in another view, but also Archer's paradox included. Archer's paradox is basically when the arrow is leaving the bow, it has a little wobble to it So it almost looks like a little sine wave oscillating, and can't really account for that with such little distance and with a video that's not pointed from straight above. So that can cause a lot of differences too. And then, like I said, the distance traveled because the video didn't show the entire field. Now for some errors, human error, there's always human error and stuff like this. The tracker FPS, if there was more frames in the video, I could have gotten it, like if it was in a very high definition slow motion video, including the video quality there. And then more precise measurements overall. Like I said, there's a lot of little things that happen on the system, and it's very difficult to account for everything, and especially because it's a unique environment. Now for the forces, we need to apply Newton's second law and the other forces acting on the system. So we have a final velocity, obviously, that comes from the total net force. And this is the big difference right here, the total net force, because there are many forces acting upon it. And then just to add one important one that we've been learning about recently, this is the inertia of a hollow cylinder. And arrows are actually mostly hollow carbon. So this is what the cross section of it would look like. But this is unaccounted for in a point particle system. And then most importantly, the projectile motion we can see through the video and then the analysis and tracker. All right, thank you very much for your time and have a great rest of the day.